We've been talking about energy. We've been talking about enthalpy thus far in the chapter. Now we need to look at entropy. And entropy gets a little difficult to get our head around at first. Notice, here's our definition of entropy. And it's talking about an integral measure of random thermal energy distribution. So it is the random thermal energy distribution within a system. That doesn't make a lot of sense, really. But I think easiest way to think of it is about randomness and about things spread out. And it's really, when we're talking about entropy, it's something, some definitions talk about energy that cannot be used. It's just the random energy in a system that used to spread things out. Another good reference is, notice, it talks about entropy increases from zero. And zero entropy would be a perfect, absolute zero place where you have perfectly crystalline ordered structures. So we have perfectly crystal ordered structures. We have a temperature of absolute zero. And anything away from that is an increase of entropy. So what do we mean anything away from that perfect condition is an increase in entropy? Well, if we have a structure that's highly ordered and compact and everything has a certain place, an increase in entropy goes to more disorder. Or, in an actual practical example, if we take our tea bags, or in this case it's talking about sugar molecules, and we put our sugar molecules in the tea, well, they're going to dissolve and they're going to spread out. So they're no longer going to be highly ordered. They're going to have a state of higher entropy. And we talk about entropy, we talk about this order in units of change in S. So if this is high entropy, if dissolving sugar goes from a low entropy to a high entropy, that's an increase of entropy. And this positive entropy is actually a favored state. So this happens, and when it's favored, that means it happens spontaneously. So the sugar dissolves. You can't the sugar is not going to recombine into crystalline sugar compounds within the liquid. It cannot. Its entropy is in its dispersion and in its randomness throughout the liquid. That's what entropy is. If we had gas, here's a system where we have gas in the corner. If we introduce gas into a system, what is that gas going to want to do? Well, the entropy is going to cause that gas to spread out. It's not going to want to stay packed in a corner. That is the randomness in the situation. That, again, it spontaneously occurs. Spontaneously, the things want to spread out. Spontaneously, things move to more. A lot of times you'll see this, and we'll talk about disorder. I don't know if it's disorder as much as just randomness and just spread outedness. Things are going to spread out. They're going to break apart. They're going to go towards a position of more randomness, and that is a favored position in our chemical reactions and actually in the universe. So when we look at it practically in chemical reactions, what does that mean? Well, the things that are more entropic, that are more entropically favored, are going to be things that are more disordered. And so if we go from a liquid to a gas, well, notice we're going to have to put energy in to boil something, but actually that is a favored state entropically. That's a positive change in entropy. That's going to be favored. If we take an aqueous sugar out of the liquid and make it a solid, that's a decrease in entropy. That is not a favored thing. That's not something that's going to willingly happen spontaneously. Now notice this one. We all have gases. So right now we've been comparing states, and basically we've said this. We've said that if we're looking at entropy, well, gas is going to be higher entropic level than liquids, is going to be a higher entropic level than solids. What about this one? Well, we have two gases, and we have gases over here. But I'm going to tell you that this is this is entropically favored. It's favored as far as having more randomness, more disorder, because notice we have two gas molecules. Over here we have one, and then three here. That's a total of four gas molecules. So the more stuff we have, the more entropic, the higher state that we're in, the more entropy that we have. Last one, if you're playing along at home, would be a decreased entropy, because we're taking a gas and then we're putting it into a liquid. So we have two things that we have to balance out now when we look at reactions and we decide whether they're spontaneous. What we said before is, if we're looking at enthalpy, which we've already done calculations with, if we're looking at enthalpy, well, negative changes in enthalpy are spontaneous, or favored, I should say. Maybe we want to say favored. We don't want to use this word spontaneous yet. So negative changes, I'll write it correctly here, negative changes in enthalpy are favored, right? So these are exothermic reactions because the products are at a lower energy state. Positive changes in enthalpy are unfavored because we have to go to higher energy states, and we have products that are at a higher energy state than the reactants. That is not favored. If we look at entropy, if we look at the level of randomness, well, it's going to be opposite. Favored reactions are going to be positive changes in entropy. The more disordered, the more spread out that thermal energy is, the more favored it is going to be. Negative changes in entropy are unfavored. So putting things together, getting rid of that random spread out thermal energy is an unfavored position. So if we want to look at whether a reaction will occur or not, or whether it's spontaneous, what we have to do is we have to balance these two things. We have to compare them. We have to compare the enthalpy of the reaction to its entropy. So we have a relationship to do that, and that's what's called Gibbs free energy. And notice all of these units are calculated. Gibbs free energy is calculated in kilojoules per mole. Enthalpy, like we've done, is in kilojoules per mole. Our entropy, I haven't shown any values on it yet, but entropy is joules per degree Kelvin per mole. So we do have a temperature component in entropy. So whether or not entropy affects the overall chemical reaction really has to do with what the temperature is. And so this is an equation we're just going to look at. One thing I need to tell you when we're at this point is that if we have negative changes in Gibbs free energy, if Gibbs free energy is negative, that means we have a spontaneous reaction. So if Gibbs free energy is positive, it's non-spontaneous. So the reaction actually cannot occur if we have a positive change in Gibbs free energy. So this is non-spontaneous. It cannot occur. We can only have spontaneous reactions that occur. These spontaneous reactions need to have negative Gibbs free energy. So what type of criteria are going to allow us to have a spontaneous reaction? Well, let's take a look here. So here's our reaction, and see if this makes sense. So no matter how these are calculated, or when they're calculated, remember, this needs to come out negative. Okay, negative means it's going to be a more favored state. So here are the ways our reaction can be favored. So if we have an exothermic reaction that has an increase in entropy, so what this is saying, it releases energy and it becomes more disordered. Notice, then our Gibbs free energy is going to come out negative and it's going to be product favored. So you can pretend putting numbers in there. Imagine, again, exothermic value. So this value is negative, okay, and this value is positive. Well, there's a negative right here. So no matter what the temperature is, if this is a positive value, this is a negative minus another value, this overall is going to be negative no matter what. So if we have exothermic reactions that increase in entropy, increase in randomness, they're going to be favored no matter what. Now if we take the reverse conditions, and let me clear the ink here. If we take the reverse conditions where we have an endothermic reaction, so we have to put energy in, well, again, that makes this a positive value. And now if we have a decrease in entropy, so our term there in the back is negative. Well, now what's going to happen is we have temperature times, so negative times negative, that's going to be positive. So we have a negative S. We have a negative value here. That's going to make it be a positive. So there's no way that Gibbs free energy cannot be positive. So it's going to be reactant favored, or we could say non-spontaneous. If it's reactant favored, it means the reaction is going to be pushed to the left. So not pushed towards products, but pushed towards reactions. It's going to be a non-spontaneous reaction. And there's no way, if we have an endothermic reaction that has a decrease in entropy, that we can have a spontaneous reaction. So those maybe are not so hard to figure out. They kind of make sense. It's exothermic. There's an increase in entropy. That would be, favored reaction. Endothermic, decrease in entropy. That would not be favored. Where it gets kind of interesting and confusing is if we don't have those scenarios. Say we have this. We have a negative value in each term. We have an exothermic reaction, but at the same time, we have a decrease in entropy. So we have a negative value here, and we have a negative term over here. So now what that is telling us is then we have a temperature-dependent condition. What that means is in an exothermic reaction, it will be favored if our temperature is really low. Okay, why does our temperature need to be really low? Well, because we have this negative value here, these two negative values, again, are going to make a positive. So if we can decrease the importance of that term, then we're going to get an overall negative value from this. So it says these are temperature dependent. Well, they're favored at low temperatures. At very low temperatures, the overall entropy doesn't matter, or the overall entropy actually is that term is reduced because of the low temperatures. And so if we have an exothermic reaction, that can be favored at a low temperature. Let's look at the next one. Now we have an endothermic reaction. And again, I'll erase my ink. And you can kind of guess that this one's probably going to be the other way around. If we have an endothermic reaction, we have a positive term here, and we have an increase in S, so that's positive. So this negative is going to count overall. So how do we get this term big enough so there's more negative than positive coming from this? Well, we need to have a high temperature. So endothermic reactions, they can occur spontaneously if there's an increase in entropy and we're at a high temperature. So these are spontaneous at high temperatures. These ones are spontaneous at low temperatures. And I believe there's a table in your book that tells you this. Here we go. So again, exothermic reactions, if we have more disorder, G is always negative, I is spontaneous. Okay, and I'll write spontaneous there. If we have exothermic reactions, but we also have more order or a negative change in S, they can happen at low temperatures. Like we said, endothermic reactions with disorder can be negative only at high temperatures. So we need really high temperatures to get that S term to be bigger. And finally, endothermic reactions that cause ordering as well are negative, never negative, or non-spontaneous. And this takes a while to figure out, but I would highly recommend that you take a look and you plug values into this so it makes sense. But we can look at a couple examples. So let's actually look at some numbers and values. And again, most of our changes in enthalpies or changes in entropies are going to be from tables. So we're going to have to evaluate what they mean. We don't derive them very often. So let's look at an example here. So we have a chemical equation. We have iodine as a solid, chlorine as a gas, making this iodine chloride as a gas on the other side. Now it says the enthalpy of formation for the iodine chloride is a positive value. Remember what that positive change in enthalpy of formation means? That means it's endothermic. And again, endothermic reactions generally are not favored. Okay? They are not favored. Because they're endothermic, we have to put energy in. However, notice the Gibbs free energy is negative. That means this equation is going to be spontaneous, this chemical reaction. Well, how could that be? Well, let's go on and answer the questions. We'll figure it out here. So it says, is the forward or the reverse reaction favored by the enthalpy factor? Well, again, the enthalpy factor is endothermic, so the reaction is non-favored. So in this case, the reverse reaction is actually favored. So I'll put reverse. Will the forward or reverse reaction occur spontaneously at standard conditions? Well, yes, it will, because of the Gibbs free energy, because Gibbs is negative. So it will. So that brings us to C and brings us to our big answer for this. It says, is the forward or reverse reaction favored by the entropy factor? Well, if the reactants are favored by our enthalpy, but we have an overall negative Gibbs free energy, that must mean entropy favors the products. So the forward reaction. That's the only way this can still go forward. So if this is saying not favored based on enthalpy, well then our entropy has to favor the reaction. It has to be, again, larger than our enthalpy so that we get that overall negative value. And let's see if we can make sense by looking at what the values are. Notice this is a solid reacting with a gas to make two gases. So that is a more entropic state because there's two gases as opposed to one, and there is no solid. So it makes sense that entropy would favor the products. So entropy favors the products, even though our enthalpy, our energy value, does not. So now it says calculate the value of TS. Okay, so TS favors the forward reaction, so our change in entropy has to be a positive value. So when is this going to occur then? Let's again look at our change in Gibbs free energy is the change in enthalpy minus T times the change in entropy. Well, again, if this is negative and this is positive term, right, because it's endothermic, well, this also is positive because it's an increase in randomness. We're forming more gases than just having a gas and a solid. When is this going to occur? Well, this is going to occur at high temperatures when this value can get big enough that this negative value takes care of all any positive value that would be there, and we get an overall negative. So this is going to be favored at high temperatures. And now really the easy part, the hard part is the theory. The easy part is doing the calculations. Since calculate the T times the change in S. Well, if we have Gibbs free energy being negative 5.4, and the change of enthalpy being plus 18, then negative T change in S. We can just rearrange this equation. 5.4 over 18, cancel out the negatives, equals T delta S. And if you do that, you'll find the term equals 0.3. Now, what the temperature is, we don't know. If we knew the temperature, then we could calculate what the entropy value is. That we don't know right now. All we're solving for is the value of that term. So one more Gibbs free energy type of problem. So it says calculate the Gibbs free energy for the following equation at 25 degrees. We have a enthalpy, we have an entropy factor. Now notice this, some things I can already tell. This is negative, so this is an exothermic reaction, and this is positive, so there's more entropy, so there's more entropic, so that means this is favored. So this overall I can determine right now is going to be a favored reaction. Hydrogen peroxide decomposing into water and oxygen is going to be favored because this is an exothermic reaction that produces more randomness. That has to be a favored reaction. And notice, here's where we can tell the randomness. We have a liquid forming a liquid and a gas. That's a higher level of randomness, higher level of entropy. So entropically it's favored, energetically it's favored. Now let's calculate the Gibbs free energy to prove it, because this, again, should come out to be a negative term if it's a favored reaction. And it is. So you have negative 196. Be careful here. Notice this is in joules and this is in kilojoules. They're going to pull that on you sometimes, those buckers. Notice minus our temperature is 25 degrees C. And you'll notice they actually wrote the entropy wrong here. It should be moles per Kelvin, which kind of gave me pause. So we have to have this in Kelvin, our temperature changes, when we do our overall changes when we're calculating Gibbs free energy. Regardless, overall I get negative 233.5, and that will be in kilojoules per mole. Well, this one I converted everything to kilojoules. Notice I did convert my entropy from joules into kilojoules. We should be able to do that. Kilojoules per mole. It's a negative value, and it's spontaneous. So I answered it right up here. That was spontaneous, but I can prove that it's spontaneous because this is a negative. Adding it up with another negative, we get a negative 233.5. So it is a spontaneous reaction.